Hello and welcome to lesson 6.1 on composition of functions. So this is the start of Unit 6, which the main topic of Unit 6 is actually about radical functions. Radical functions are like square root, cube root, x, and stuff like that. But we actually spend the first 2 days to talk about composition of functions and inverse functions to kind of lead into square root and cube root. So while this topic right now is not about radical functions, it kind of, we'll get there. Yeah, it leads into it. So to start us off, in class I did like a little warm-up. You said like, oh, you know, if f of x is like x squared plus 1, then what was like f of 3? And you say like, oh, well, that's like 3 squared plus 1, which is like 9 plus 1, which is like 10, right? But then I would say like, oh, okay, well, what's f of like x minus 2? You say, well, okay, well, f of x is x squared, then f of x minus 2 is, plus 1, is x minus 2 squared plus 1. And then this you'd have to expand. You can say, okay, it's x squared minus, not 2, but x squared minus 4x plus 4 plus 1. And that gets you x squared minus 4x plus 5, right? Anyway, that's just background of what we did at the warm-up during class. But the idea was that, you know, I had some function f of x equal to some quadratic thing. And then I said, well, what if I made the input a linear function like x minus 2? Right? What if I do that? And, you know, x minus 2, that's a linear function. You could call that its own function, g of x. So establish that g of x is x minus 2. And so what this means is you're plugging a function, g, into f. And so we write that as f of g of x, like that. And so that's kind of what the topic is in this video, is putting functions into other functions. And so I encourage you to kind of just pause the video and read this for yourself, try to make sense of it. I am going to briefly talk about it, but it's just formal academic language establishing what composite functions are, kind of an official definition of what they mean. Yeah, so feel free to pause. I'll go ahead and explain it, though. Definition says, let f doing what? The heck is that? Is it f with a colon and then an a and then an arrow and then a b? What does that mean? Well, if you read these bullet points down here, these kind of help you figure out how you read this. But f with this colon a b, this establishes f as a function mapping elements from a domain A to a codomain or range B. Codomain is probably more accurate, but for our intents and purposes, you can just call it range. And this is read f mapping A to B. So when I write f colon this, right, this is read f mapping A to B. That's what it means. Then this is a function g mapping B to C. So you'll notice that A is taking, this is a domain up to a range, and then B is the range that was here, but then we're mapping that to something new. And B is actually the domain of G. Anyway, I always stumble on saying this because I'm trying to say composite or composition. You say composite versus composition. You say them differently, right? Anyway, the composition function of f and g denoted by this, it's just a circle. It's not a time symbol. It's not like g times f, it's g composed with f. It's defined as g of f, or g composed with f, maps A to C, and is given by this. So when you see this symbol, g composed with f of x, we interpret that as g of f of x. It means put the function f of x into the function g. And then this little part here says for all x in A. All that means is this is true for everything in your domain. So everything from the original domain you started in, it gets mapped to C, essentially, okay? And yeah, that's the formal academic definition of composite functions. By the way, this notation is sometimes used for other operations of functions. So like this is composition, but addition of functions like g of x plus f of x, right? You could write that as g plus f in these parentheses of x. So that's one way to write that. As well as if you multiply them, so this is a filled in dot, g of x times f of x, you could also write that as g times f of x. It's just kind of a shorthand way of writing these things. Okay, and here's a visual of kind of what's going on. So you can see the sets A, B, and C. F, and this is where I'll sort of start annotating permanently now, F is mapping A to B, right? It's taking stuff from A and creating a pairing with some element in the set B, right? And then G is doing the same thing. It's taking stuff from B, it's mapping it to C. That's what it's doing, right? But the question is, what is F of, or G of F doing, right? G composed with F of X is G of F of X, which is mapping A to C. So, in fact, maybe I'll switch colors here to write that. G of F, or sorry, just, I don't need the parentheses. G of F maps A to C, which means it takes stuff from here and maps it over here. Yeah? So we're going to follow this line of these arrows, and you'll find this pretty easy to follow. If we look at f of 1, right, all that means is if I input 1 in the domain of A, where does it go in the range B, right? Well, I put in 1 and it maps to 3. So f of 1 is 3. I mean, this is basic Algebra 1 kind of introduction of functions, right? G of 3 means, well, I'm going to take 3 because I'm using the function g, which maps B to C. So I'm not looking at 3 here because that 3 is in A. This 3 is in B. So then G of 3 takes 3 and maps it to 4, right? You say, Mr. Spake, this is very easy. It's taken a long time to explain. But this is the foundation of functions and composition of functions, right? Now, what if I take the composite value G of F of 1? So what that means is, say G of F of 1, you kind of work from the inside out. So look at your interior function. I want to analyze F of 1, right? Because remember, G of F starts in the domain A. So F is mapping A to B, means we're going to look at 1 in A. So F of 1, you know, we said that that maps to 3. So I can replace F of 1 with a 3 inside of that sort of composite function value. G of F of 1 is G of 3. And as we just said right here, G of 3 maps to 4, right? And so that means, right therefore, G of F of 1 equals 4. And of course you could see that right here because 1 goes to 3, which goes to 4, means 1 goes to 4 for the composite function. So that's your pairing, right? Again, you can think of all these as ordered pairs. So like this is 1, 3, this is 3, 4, but this ordered pair is 1, 4. Because what you started with in the domain was 1, but the finale, like the range was C, and then ended at 4. And then if you look here at G of F of 3, you say, okay, well, F of 3 maps to 9, and G of 9 maps to 36. Written out, right, G of F of 3, F of 3 maps to 9, so G of 9 equals 36. And so I can put 36 here. And so that point is 3, 36. Yeah. And maybe a few things to note here is that I'll put this in yellow perhaps. You know what? I'll color code this just because I'm going to color code this. So I started in red, right? Over here, A, this set was the domain of F. And the set B was the range of F. But the set B was also the domain of G. So this is the domain. Oh, I shouldn't be doing it in yellow. That's what I should be doing. This is the domain of G, and then this is the range of G. And now think, okay, well, the composite function starts in A, so that's the domain of F composed with G, but it ends, right, in the set C, so that's the range of F composed with G. As you kind of see the relationship between these sets, okay? I'll be saying this is a lot to say about a very simple thing, Mr. Spake. I say yes, but again, it's the foundation of functions. If you can understand how these mappings work, it'll be really powerful later on. You do revisit this topic again in pre-calculus, and you'll start to really care about domain and range and all that. Okay, so now on to some tables and things like that. So it's pretty common when you're teaching composition of functions to teach students how to follow composite function values through a table or a graph or things like that. It's just good practice. It kind of makes you think about what's your input, what's your output, what's your domain, what's your range, where is it coming from, where is it going, right? It's just general, beefs up your knowledge of how functions work, yeah? So composition functions, we're going to use this table of values to evaluate each expression. So you have the table of values here, right? This is F with X, and then G also with X, right? And so I say, okay, let's look at F of G of 2. So, say red, F of G of 2. So again, as I said earlier, you look at the interior first. So I look at G of 2. And what that means is X equals 2. What does G of X equal? Or in other words, what is G of 2, right? So I look at the column for X here at 2. 2 maps to G of X, which is 1. So 2 maps to 1. So that tells me that G of 2 is 1, means I can replace that with 1 inside of F. It's F of G of 2, so now it's F of 1. And now what was the output for G was 1, is now the input into F. So I go back to the X column, and I look at 1, which maps to 2 in F. So F of 1 is 2. So F of G of 2 maps to 2. That is our value, right? I started with 2, but then I ended with 2, okay? And then I gave some class time for students to kind of work on that. So I encourage you to pause the video and really just try it for yourself, see if you can figure it out. And if you do, then you can skip ahead, right? You can check your answers, you'll be good. But I will go ahead and explain everything just in case you're struggling on how this works, okay? Practice helps the repetition. You'll start to see patterns. So G of F of 2, okay, well, I guess we'll do that in blue. G of F of 2, right? I start with 2 in X, because that's the input, right? So I start with 2, and F of 2 goes to 0. So then I'm looking at G of 0. Now 0 is the new input, so I look at when X is 0, and that maps in G to 0. So G of 0 equals 0. Means G of F of 2, you start with 2, but you end with 0. Okay? And then, you know what? I'm going to lasso this. Move that over there. Take this, go to yellow. And then let's look at F of 3. like so. So I say, okay, well, f of 3 means I start with x, which is 3, and that goes to 1. So then f of 1, and now I just look at this again. But, hey, I already said it over here. F of 1 is 2, right? So f of 1 goes to 2 means I end in 2. And we're just going to keep on doing this, yeah? Go back to red. We're going to look at g of f of 4. So f of 4 means I take x as 4, and I map within f to 4. So I've got 4. Now, you're still, so this 4 goes back to here, because it's still x, because it's the input now, it's x, and then 4 maps to 2 in G. Does that make sense? I don't know if that was confusing. 4 goes to 4, then you return to 4 as the new input, and that 4 maps to 2 in G, because you're doing G of 4, since f of 4 is 4, and G of 4 is 2. So, then this is 2. I hope that's not confusing. It's a relatively straightforward idea, but as one student put it, it's confusing, but I kind of get it. I like that phrasing. G of 1, I say, okay, G of 1 is 4, and G of 4 is 2. Oh, look at that, right? Same idea. You say G of 1. G of 1 goes to 4, so that means it's G of 4, but 4 goes to 2. So G of 1 is 2. That's right, right? I think so. G of 1 is 4. G of 4 is 2. Okay, yeah. Looks good to me. And then last one, taking our time here. Feeling good. F of G of F of 0. Cool. So work on the inside out, right? So start with f of 0. So you say, okay, 0 maps to 3. And so that means it's f of g of 3. So then 3, using the function g, maps to 3. So then that's f of 3. And then 3 maps to 1 in f, which equals 1. So then I end with 1 here. 2, 2, 1. And that is it. We did it. All right, so that's how you do it with tables. And then after this, I kind of moved on. It just gave this to the class to work on. Excuse me. But it's a little bit different because it's kind of like I was going to say scatter plot, but it's really, I mean, I guess that's what it is. It's just ordered pairs plotted, a graph of points. So it's the same premise as what we were doing up here, just finding a table of values. But you have to figure out what this table is. Now, I do encourage you to pause the video and try both this and this, okay? But, yeah, that's up to you. So I'm going to go ahead and explain how it works. F of g of x, in this case, right, f of g of x, we're starting with g as the input, and then we're going to f. So if I were to make these kind of little ovals again, right, little ovals, g is taking stuff from this set A to B, and then f is taking that stuff from B to C, yeah? But the g values, right, what am I saying? The domain of G, being this set A, is what you start with, is this. That's A, right? This is the set A, and it maps it to B, so that's the set B. So you can see, like, okay, A is like -3, 0, 2, 5, and 9, right? That's what's in that set. And then we're going to take it to this, and, well, there's kind of two ways you could think of it. Well, so F is mapping B to C. And when we read graphs, the x-axis is the domain axis, right? These are the x values. Those x values are the set B. And I guess I don't know why I changed colors there, but I guess it doesn't matter. And the y-axis, right? Let's just say x-axis is B. And the y-axis is C. And so the coordinates, right, is really just the table. All right, this is just a table as in graphical form, right? If you want, you can make a table of this. So I can say x and f of x, where this is the set B and this is the set C. And I'm going to lasso that and move it down a little bit, like so. All right, now I don't like that. Take you back up. There you are. So oh my gosh, it's not A, it's B, and that's C. Because you see, F takes stuff from B and goes to C. And so you say, okay, well, what's in F, right? The x values. So we're going to go from coordinates, right? The first point here is 0, -2. So 0, -2. The next point here is 1, 2. The next point, which is here, is 2, -5. So 2, -5. The next point, as you'll see, is 3, 0. And the last point is 5, -1. Okay. You don't have to make a table. You can just go using the table to here. But the table might help you if you're struggling to follow along with some of this stuff. But what I wanted you to notice is the values in this column and the values in this column are the same. 0 and 0, 1 and 1, 2 and 2, 3 and 3, 5 and 5, right? That really confirms that the domain that F is taking on is the range of G, right? So that's shared. So you could even say this is the range of G of X. And the y-axis is the range of F of X. We're getting really technical here. Yeah, there's probably more than what most people do in Algebra 2 on composition, but I don't care. I think it's interesting. I think it's kind of cool to think about and talk about. Anyway, let's do these mappings now. As you can see, I'm going to do this in yellow. If you remember, so what does f of g do, right? F of g of x maps A to C. So the set A, right? This is the set A. Let me lasso this, get it out of the way. This is the set A, and this is the set C, right? But I can't just put random numbers in there. I have to actually follow the mapping. But everything in A should map to C based off this composition, right? So this column of A is the same as this column of A. So I just copy down those x values, -3, 0, 2, 5, and 9. And I just follow throughout the table, right? I'm going to start with -3 in A. So -3 goes to 2, and then I look at 2 in B, 2 goes to -5. So I ended with -5 in the set C, which means that's the point here, right? So I got from -3 to -5. I just keep doing this. So as I start with 0, 0 goes to 5 in B, and then 5 in B goes to -1 in C. So that's -1. That's that mapping. 2 goes to 0, and 0 goes to -2. So that's -2. 5 goes to 1, and 1 goes to 2. And 9 goes to 3, and 3 goes to 0. So put the 0 there. And ta-da, you've done it. You've mapped everything, right? And notice that the set C's are the same. This negative 5 is this negative 5. This 2 is this 2. This negative 2 is this negative 2. This 0 is this 0. And this negative 1 is this negative 1. The entire range of C was used. Yeah? It's kind of cool. I like it. And again, when you end up taking pre-cal, your understanding of composition functions will continue to build. Especially by the end of Algebra 2, once you've learned all the functions of algebra, of Algebra 2, then, you revisit composition of functions later in math, and you get to do even more with it, which is cool. It's fun. Okay, I recommend pausing the video and trying out these. I will kind of label out which is which. Remember that the x-axis is the domain, so we could call that the set A, and then we can call the y-axis the set B, because that's your range, right? So that's the set B. And then the x-axis on this graph is going to be the set B, but the y-axis is going to be the set C. So that's C. And then again, so for this graph, the domain, meaning the x-axis, is the x-axis you started with, A. But the range is the range you ended with, which is C. So this is the set C. Okay? Now, if you want to make tables, you're totally welcome to. I'm not going to. I'm just going to do it. Okay? So negative 2 is, 0, comma, negative 2. So I started with 0, and then it's going to negative 2. Now on this, it's negative 2 on B. So now I look at B as negative 2, which is 0 at C. So I started with 0, it went to negative 2, and negative 2 went to 0. So the ordered pair is 0, 0. Okay? That's 0, 0. You know what? I might make a table because it might be easier for you to follow, just in case. So this is x, this is g of x, this is set A, this is set B. And so I'm going to just put these points, 0, negative 2, 1, comma 2, 2, comma negative 4, 3, comma 0, 5, comma negative 1. And then on this one, x and f of x, where this is the set B and this is the set C, you've got negative 4, 3, negative 2, 0, negative 1, negative 3, 0, 1, and 2, 4. And then this last table, x and f of g of x. By the way, if you get this and you don't need this, just skip around the video. It doesn't matter to me. I don't care. This x comes from the set A, and then this is the set C. So I'm going to copy down the set A from the table on the left in red. And then I'm going to find these values by actually going through the mappings, right? So the next point would be 1. So 1 goes to 2. Then I look at 2 on this axis, which goes to 4. So 1 goes to 2 and 2 goes to 4 means 1 goes to 4. Sorry, 0 went to 0, right? Again, you can see that with our tables here. 1 goes to 2 and 2 goes to 4. So 1 goes to 4. And so I'm going to plot that as a point 1, comma 4, which is right here. Okay. The next one. 2 goes to negative 4, and negative 4 goes to 3. So that means 2 goes to 3. So yellow. 2 goes to 3. So it's 2, comma 3. Now where does 3 go? 3 goes to 0, and 0 goes to 1. So 3 goes to 1. 2, 3 goes to 1. Oops. This makes this point right here. And lastly, 5 goes to -1, and -1 goes to -3. So this is -3, and I plot 5, comma, -3. And that's it. We did it. And again, you can see that the entire range of C was used. 3, 3, -3, -3, 1, 1, 4, 4, 0, 0. Okay? And there it is. That is dealing with those. And you'll find on the homework that you'll have some graphs to do. So I'm going to hand you some graphs that are like this. So you have to find the points on it, but it's the same, it's the literal same thing as these graphs, okay? No different. Okay, let's go on to writing and evaluating composite functions. Yeah, oh man. By the way, I took way longer to explain that here than as opposed to in class, but you know, it's for help, right? Yeah. Okay, writing and evaluating composite functions. Let's do this. So I got blue, got my red. This is just talking about writing the functions together. So kind of what the warm-up was like, where you put a function into another function. This is the main thing you really need to know for Algebra 2 purposes. But that other stuff is pretty useful kind of in like calculus, pre-cal, calculus, and then just general theory about functions in math. But anyway, so we're going to start with two functions, f of x and g of x. So we got 2x minus 3 and 1/2 x squared. Let's write the function h of x if it is defined to be the composition of f with g, which is to say f of g of x, right? So let's say, okay, what is this? Well, f of g of x, and you can write these two ways. I don't really care which way you write it. I'm going to show you both, one for example A, one for example B, and you choose which one you like. For the first one, I say, well, f of g of x means, you see, f of x equals 2x minus 3. So f of g of x, you replace x with the input g of x. Means it's 2 times g of x minus 3. Now, what is g of x, right? G of x is 1/2 x squared from up here. So I replace g of x, right, with 1/2 x squared, and then I do that minus 3. Now I can multiply that too. 2 times 1/2 is 1, and so I get x squared minus 3 as my answer. So the composite function, h of x, is x squared minus 3. Okay? That's one way to sort of write that. And then you say, okay, what is h of 4? Well, you put 4 in for x. So you say 4 squared minus 3. Since we found the composite function, that's 16 minus 3 is 13. Done. Okay? Another way you could have done that. So h of 4 means f of g of 4. And I'm showing you this for a reason, not just for fun. It is for fun, but it's not just for fun. It's also to know how to do it another way. Instead, if you don't want to find the composite function, in other words, if I didn't ask you for this, and I just asked you for h of 4, given this composition, without actually finding a composite function, you could still find this by plugging the point in to these functions. So you say, okay, well, f of g of 4 means I plug 4 in for x into this function. So I say, okay, g of 4 is 1/2 4 squared. So that's 1/2 times 16, which is 8. So then this is equal to f of 8. But then f of 8, right, means you plug in 8 for x here. So it's 2 times 8 minus 3. There it is. There's your 16 minus 3, which is 13. Yeah? So that's another way to do it, and I do want you to know how to do that, okay? It's important. Let's say put a star on that, okay? Now let's write the function j of x if j equals g composed with f. So say j of x is g of f of x. Here's the other way to do these. So f of x we can replace with the definition, right? This is g of f of x, which is this, 2x minus 3. So then I'm plugging in 2x minus 3 in for x squared. So it's 1/2 2x minus 3 squared. What I did here is essentially the same thing. It's just here I plugged in the general idea of g first, then I replaced it by the definition of g. Here I'm just directly replacing g with what it is, f with what it is, and then replacing x with that function directly. I don't care which way you write it, it's fine. And maybe, I mean, we could stop there, but it'd be a good idea to expand that, right? 1/2 times 4x squared minus 2 times 3 is 6, double that is negative 12x plus 9, which comes out to, so I'm not missing anything, am I? Oh, no, I'm not, I'm good. I get 2x squared minus 6x plus 9/2. Okay? Ta-da! And that's the function, right? I mean, it would be fine. It would be somewhat acceptable to leave it in vertex form here. It's okay. It's not the worst. But, you know, I'm going to write it in standard form. And then if you want to find j of 1, right? J of 1, well, j of 1 means g of f of 1. So we got to figure out what f of 1 is, right? F of 1 is 2 times 1 minus 3. It's 2 minus 3, which is negative 1. So then this is equal to g of negative 1. But g of negative 1, you plug that in, and you got 1/2 negative 1 squared. So that's 1/2 times 1 is just 1/2. So I end up with 1/2. And it works. I can do the exact same thing here by plugging in 1 for x. 2 times 1 squared minus 6 times 1 plus 9/2. Well, that's just 2 minus 6, which is negative 4. And so you do negative 4 plus 9/2 is 4.5. So that's 0.5, which is 1/2. Okay? Same thing, whatever. But hint, hint, you want to know this method for the quiz, because you're going to get something that you don't want to expand it. You just want to plug in the numbers. Way easier to do that. Okay? All right. Now on to student practice. So this is just for you to do. I would pause the video and try these. Yeah, just kind of practice getting used to composition functions. I'm just going to kind of go ahead and do them here and explain as I go along. So we want to find the composition of each. So I say f of g of x, right? So here's what I would do. I say f of x is absolute value x, right? So f of g of x is absolute value g of x, right? But what is g of x? G of x is 2x minus 3, given right there. So this is the absolute value of 2x minus 3. And that's it. You're done. Right? I can't really simplify that any further. It's just an absolute value function. Now let's do g of x, right? So g of x is 2x minus 3. So g of f of x is 2 times f of x minus 3. But what is f of x? It is defined to be absolute value x. So I say 2 times absolute value x minus 3. And I just box that, and we're done. That's composite functions for you. And so notice these aren't the same thing, right? This is different from this. This will never be negative. This could be negative since you could subtract 3 from a smaller number. Okay, now we look on to the next one. Same thing, right? We're just doing the composite functions. F of g of x. You say, and I'm going to write this the other way, right? Okay, so f of x is 2x squared minus 1. Now, g of x, so say f of g of x is f of, sorry, can I use more space? I don't have more space? Okay. F of g of x equals f of square root x plus 4. So f of square root x plus 4, right, is a 2 times square root x plus 4 squared minus 1. And by the way, when you take square root of happy face and you square it, you get happy face. Okay? It undoes it, right? Square root and square is inverse operations. You get the same thing out. Okay? So this is 2 times x plus 4. You just drop the, keep the parentheses because 2 just distribute, but I don't need the square root of the square anymore. Distribute 2x plus 8 minus 1 is 7. And that is it. That's the composition. Okay? Now I did the same thing. Do g of x, square root x plus 4. So g of f of x is g of 2x squared minus 1. So g of 2x squared minus 1 means you're plugging that in for x here. So you've got the square root of 2x squared minus 1 in parentheses plus 4. Because see, remember, whatever is in these parentheses, right? If it was g of star, it would be square root star plus 4, right? So we're replacing x with the function f, which is this. So x becomes this right here, but the 4 doesn't go anywhere. And then simplify this down just a little bit, you get 2x squared plus 3. And that's my composite function. Yay! We're doing great. It's a long video. My goodness. Long video for what should be, hopefully, a simple lesson, but I don't know. Okay. Number 2. It's starting to get late, guys. I'm getting sleepy. So you got this one here. I made up this problem for fun. Just see what you can do. Just having fun with this. Suppose you knew a point on f. So f of 6 is negative 2. And you say g of x is 2x plus 5. So let's find g of f of 6, right? So g composed with f of 6. And you're supposed to, in class, you were supposed to do these on your own. So again, I recommend pausing and trying it for yourself. G of f of 6, well, let's say it says g of f of 6. We are given that f of 6 is negative 2, right? So I can replace f of 6 with negative 2. And then I'm just replacing, the way functions work, right? G of x is this. You're putting in negative 2 into this function. So this is equal to 2 times negative 2 plus 5. That's just negative 4 plus 5, which is 1. So conclusion, therefore, right? G of f of 6 gets you 1. Box. I don't like the trapezoid, and you know this. Okay. Now part B. And this was more tricky. It's a little tough, this one. just interpreting what's going on. It says if G composed with f of 3 is 1, what is f of 3? The thing is, you don't have a definition for f, right? You can't plug 3 into anything because we don't have an equation that establishes what f is. And you really can't use this to find an equation for f either. So the way you're supposed to do this, you say, okay, look, G composed with f of 3. All that means is G of f of 3 equals 1. Now notice G of x was 2x plus 5. But then that means G of f of 3, do we know what f of 3 is? No, we don't. That's what we're trying to find. So I plug in f of 3 in place of x. It's 2 times f of 3 plus 5. But we know that G of f of 3 is equal to 1. And so what you're going to do is you're going to solve for f of 3 based off this equation. And this is really just kind of like a linear equation that you're solving, right? Essentially what you have is 2 times f of 3 plus 5 equals 1. So take off 5 from both sides. 2 times f of 3 is negative 4. And then divide both sides by 2. You get f of 3 is negative 2. And they can't see it. We did it. So really the idea behind this question is just like treating this value, which is unknown. It's an unknown constant, right? F of 3, you don't know what that is, but you're trying to find it. So instead of saying like x or k or something like that, you're treating this as a single value that you are trying to find. Anyway, I just thought that was fun. Okay, last page here, and this is the setup for the next lesson. So this will lead us into lesson 6.2 on what's known as inverse functions, and that alone as a title might be telling, but we're just going to do it. So here we go. It says think about it. So fill out the table of values for the composite function f of g of x, right? So say, all right, let's go ahead, let's follow the table, right? The domain is, again, right, notice this set is the same as this set, and so we're just going to follow it like we've been doing. 1 goes to negative 4, so now I look for negative 4 here. Negative 4 goes to 1. So when I start with 1, I end with 1, okay? 3 goes to 2, and then I look for 2 in the x column. 2 goes to 3. Oh, interesting. So 3 ends up going to 3. I say, okay, 7 goes to negative 1, and negative 1 goes to 7. Okay, I'm starting to see a pattern here. I start with 7, I end with 7. And I'm going to guess that the other two are 10 and 12, but let's verify that, right? 10 goes to 9, and 9 goes to 10. Okay, that's true. And 12 goes to 5, and 5 goes to 12. Okay, looks like that's right. So, what's going on here? Like, what's happening, right? Well, I say, I'm starting with this domain A, like 1, 3, 7, 10, and 12. And then this is getting mapped to B, which is negative 4, 2, negative 1, 9, and 5. And then that is getting mapped to C, but C is 1, 7, 3, 12, and 10. And you'll notice A is C. You see, You see, I go from A to B, and then I go from B to C. But the set C has the exact same elements as A, and the pairing is just kind of opposite. 1 goes to negative 4 goes to 1. 3 goes to 2, and 2 goes to 3, right? I say, oh, So do I actually need that set C? Well, I could just say it's 1 goes to -4, and then -4 goes back to 1. 3 goes to 2, and then 2 goes back to 3. That's kind of what's happening here, right? So if this is some function, a g, this is g doing this is some function f doing this, you could also visualize this as the set A is the same as C, so G takes things from A and puts them towards B, but then F takes them back. Interesting. So you could say, right, to really formalize it, right? 1, 3, 7, 10, and 12. That's A. G takes stuff from A and maps it to B, which is 1, 7, 3. Oh, no, sorry. Just -4, -1, 2, 5, and 9. But then F takes it back. So G, right? You'll notice this function G is mapping A to B, but the function F is mapping B to A. These are just observations, by the way. These are, I say, what am I supposed to make of this, Mr. Spake? Nothing for now, really. Just observing what's happening, right? What's going on? It looks like things are going back to where they started, right? So I say, what do you notice? How would you describe the relationship between F and G? Well, they seem backwards. They seem backwards or reversed. Proper word would be inverse. Proper word. The values are inverted or inversed, right? That's kind of what's happening. You're going back, right? It's reversed or inverted. And so we're going to use this word inverse. So it seems like whatever G does, whatever G is doing, F is doing the reverse. Or in other words, F undoes what G does. Does that make sense? Right? That's kind of what is happening here, right? Whatever G does, F does the reverse. And so this is what's meant by inverse functions. Okay. And now we're going to look at the composition. I'm going to switch to blue just for fun here. So it says, given the functions f and g, we're going to write the compositions g composed with f and f composed with g for both functions. Okay? So I'll do part A, and then again, this was classwork, so I would just pause the video and try it for yourself. F with g of x. So if I'm putting in g of x for place of here, this would be equal to 2 times g of x minus 6. But g of x, as we can see, is 1/2 x plus 3. So then this is 2 times 1/2 x, that's x. 2 times 3 is 6 plus 6. And so this is x plus 6 minus 6, which equals x. Oh. Interesting. Now let's look at the other one. So say let's look at g of f of x, which would be 1/2 times f of x plus 3. You say, where are you getting this, Mr. Spake? What the heck? Where is he pulling this? Is this? Don't forget this. It was a common question in class, so I just thought I'd point it out. You say, how did you know what f of g of x was? Well, I knew what f of x was, and I just replaced x with g of x, right? This is the same as this. You're just replacing x with g of x right here, okay? And then I'm doing the same thing for this. So 1/2 times f of x. What was f of x? It was 2x minus 6. So I say that's 1/2 times 2x minus 6 plus 3. Let's distribute that half. A half times 2x is x. A half times -6 is -3. And I get x again. I want to say, right? See, it's like a little smile. I say, that piqued my interest, right? It's like a little slight smile. Now that's too much of a grin. It's like, it's very slight, right? It says, it's like, interesting. Okay, so let's move on to the other one over here. We're going to do the same thing. I'll just do this in, I'll stick with blue. F composed with g of x. So f composed with g of x is, we're going to put g of x in place of x for f. So it's cube root of x, but it's not x, it's g of x minus 5. And then we'll directly replace g of x with the function definition, which is x cubed plus 5 minus 5, right? This is this, okay? Now, cube root of x squared, x cubed plus 5 minus 5, well, that's just cube root of x cubed, because 5 minus 5 cancels. And, as we know, the cube root of x cubed is x. Oh. I say, that's interesting. I say, okay, let's draw another line. Let's do g of f of x equals. So I say, okay, g of f means we're taking this and putting it into g. So you're doing f of x cubed plus 5. But f of x, we said, was the cube root of x minus 5. And that's getting cubed, then added with 5. But if you cube a cube root, if you take a cube root of happy face and you cube it, well, that kind of looks cute, doesn't it? That looks like a happy little cube. If I cube it, then I just get the happy face, right? So what's left here is just x minus 5 plus 5. And that just comes out to x. Ta-da! Now, this is special, right? What's going on here, right? Really look at your functions, f and g, right? This function g, when you put it into f and you apply that 2, it gets rid of everything f had on it, right? This 1/2 ends up canceling this 2, but the 2 distributes to the 3, and then that makes a 6, and then the 6 combines with that to make 0. And so it's gone, right? And the same story is going on over here. You have a cube root, which is getting sort of canceled or eliminated, nullified by this cube, and you have this minus 5, which is getting nullified by this 5. And it's all going away, right? So what I notice is, right, I notice that, you see, well, f of g of x is x, and g of f of x is x. I say, f of g of x equals x, and g of f of x equals x. The functions, f and g, and these are really your own observations, but I'm just kind of giving you an idea of what student observations were during class. The functions f and g did sort of opposite things. They undid each other, right? everything that one function did, the other function did the reverse. They undid each other or one another. And notice you started with x. You started with x. Sorry, with x as the input, and we got x as the output. So these are just general observations that we're making about these functions. And then this is the definitions that you want to know and star and memorize. This special property is about inverse functions. Inverse functions are functions that undo another function, okay? And such functions that are, I guess, undoable are called invertible. You see, undoable is a terrible word, right? That's why I have better vocabulary for this. So say if function f is said to be invertible, which means, well, what does it mean? It's said to be invertible if there exists a function g such that when you take the compositions, f composed with g of x, you get x, and you take g of f of x, you also get x. This is what is meant to be invertible. It means g is some function that does all the opposite stuff that f does. It does all the reverse, the inverse of f, and you end up with what you started with, right? This function g is called the inverse. So, and you can call f the inverse of g as well, because if it's true for one, it's true for the other, right? It goes back and forth. But essentially the idea is, if you take the composition of two functions and they both come out to x, the conclusion you can make is that the functions are inverses of one another. And we're going to talk about inverses more in the next lesson. But that is it for this one. This was a chock-full lesson, but I think a pretty good one. I hope I didn't go too slow or fumble or confuse you at all, because I don't know, sometimes I worry I do that when I start rambling on. But yeah, I hope you enjoyed the video. I hope it was helpful, especially if you were struggling following this in class. And yeah, thanks for watching. Take care, and I'll see you around.